It's 3 in the morning, and a sleepy developer types one wrong number in a firewall rule. In 12 minutes, the company's entire customer-facing application is down, costing the business a fortune every minute it stays offline. This isn't a fictional story. It's the kind of fat-finger disaster that happens every day in cloud consoles. Last time in this series, we locked down your cloud with IAM and compliance controls. Too bad you can't IAM protect against a tired typo. That's why today, in Part 10 of the GCP Fundamental series, we're covering the complete DevOps, CI/CD, and infrastructure as code toolkit on Google Cloud. The tools that turn manual console clicking into peer-reviewed code, automated testing, gated deployments, and infrastructure that rebuilds itself with a single command. No more 3 a.m. panic deployments. Let's build a system that catches your mistakes before they catch you. At its core, DevOps is about breaking down the wall between the people who write the code and the people who run it. Before DevOps, a developer would finish a feature, toss it over to operations and say, "Works on my machine, your problem now." Operations would then scramble to install dependencies, configure servers, and troubleshoot crashes they'd never seen. That handoff was slow, stressful, and full of bugs. DevOps flips that. The same team that builds an application also owns running it in production. They use automation, monitoring, and shared tools to make releases boringly routine. On GCP, that means a pipeline where every code push is tested, packaged, and deployed without a single manual step, a cultural shift as much as a technical one. GCP gives you a ready-to-use toolchain that starts with source control and ends with live monitoring. Here's the flow. First, Cloud Source Repositories gives you fully managed Git repositories that integrate directly with your GCP project. No servers to manage. When you push code, Cloud Build automatically runs your build and tests. The output, whether it's a Docker image or a jar file, goes into Artifact Registry for secure storage. From there, Cloud Deploy orchestrates the promotion of that artifact through defined environments, such as staging and production, with approval steps to protect your releases. And Cloud Monitoring watches everything, feeding logs and metrics back so you can spot issues before your users do. That's the whole loop designed so you never have to click around the console to deploy again. Cloud Source Repositories is your fully managed private Git host on Google Cloud. It supports all the Git commands you're used to: clone, push, branch, merge, nothing new to learn. You can mirror repositories from GitHub or Bitbucket, which means your existing code stays in sync while you gain GCP native superpowers. And the killer feature, it integrates directly with Cloud Build, so every push can trigger a CI pipeline automatically. Pricing is based on usage. For solo learning or small teams, you'll mostly find it very cost-effective. That's one less service to spin up yourself. So why mirror your GitHub repo when you can just keep using GitHub? Because mirroring lets you stay in your usual workflow. You still push to GitHub, and Cloud Build can be set up to react to those pushes, making your CI loop tight. Your builds run inside Google's global network, reducing latency. And you unlock deeper GCP integrations. You can use cloud logging to view production logs alongside source code because the repository is linked to your project. Let's walk through it in the console. Navigate to Cloud Source Repositories. Click Add Repository. Select Mirror a repository, then connect your GitHub account to authorize access. Now your repository is mirrored, and Cloud Build can respond to your pushes. Let's cement that. The service that replaces manual local builds with automated, consistent cloud builds is Cloud Build. It's not just a tool. It's the engine that runs your CI pipeline. Remember, every push to your source repository can trigger Cloud Build automatically, so you never need to manually run tests again. Recall and review. First, what two external Git hosts can you mirror into cloud source repositories? And from part 1, what gcloud command displays your currently active project? Here's a conceptual cloud build.yaml illustrating how you can automate testing and containerization. A typical pipeline installs dependencies from a requirements file, then runs your test suite. If any test fails, the build stops right there. Next, it builds a Docker image, tagging it with the commit eshe for traceability. Finally, the images list tells Cloud Build to push that image to Artifact Registry. Put a file like this in your repo, add a trigger, and you've got a professional CI pipeline in minutes. Let's zoom into each phase of that build. First, unit tests. Cloud Build spins up a Python 3.11 container and runs PyTest. Because this runs on fresh, identical infrastructure every time, there are no "it worked on my laptop" surprises. If tests fail, the pipeline halts immediately. Fail fast. Next, if tests pass, the Docker build step kicks in. It uses the commit sha as the image tag, creating an immutable snapshot of that code version. Finally, the push phase sends the image to Artifact Registry, where it's stored, scanned for vulnerabilities, and ready for deployment. This three-step heartbeat is the core of CI. Tiny, automated, and ruthless about failures. Cloud Build triggers let you define exactly when a build should start. 3 options cover nearly every workflow. 1. Push to a branch, the most common, so every commit to main or a feature branch triggers a build. 2. Pull request creation, useful for running tests before merging. 3. Tag push. When you tag a release like v1.0.0, you can kick off a production-grade build with that tag. But here's the mistake I see beginners make constantly. They configure a trigger for feature branches but forget to add one for the main branch. Then they merge a pull request, expect an automatic build, and nothing happens. Your main branch deserves the same CI love. Use this checklist the next time you set up a project to make sure you haven't skipped it. Let's walk through setting up a Cloud Build trigger right in the GCP console. First, navigate to Cloud Build and select Triggers. Click Connect Repository, then choose Cloud Source Repositories as your source. After authenticating, pick the main branch and point to your cloudbuild.yaml file. The repo root is a common place for it, though you can specify any path. Hit Create and you're done. In under 5 minutes, any push to main will kick off an automated build. Quick checkpoint. After Cloud Build successfully builds your code, where is the resulting image or artifact stored for safekeeping? Pause and think. The answer: Artifact Registry, GCP's managed container image and package repository. Think of it as the secure library for all your built artifacts. Artifact Registry is GCP's unified home for all your build artifacts. It stores Docker images, Java Maven packages, NPM modules, Python packages, and more. Each format is versioned and kept secure. If you're still using the previous container registry, GCP recommends migrating to Artifact Registry to take advantage of the latest features. One place, all artifacts, fully managed. Turn on vulnerability scanning and Artifact Registry becomes your security shield. Its built-in scanning inspects each image push against known vulnerability databases. If a critical issue is found, like a log4j type vulnerability, it can be flagged in the console. You can then gate deployment with binary authorization, so no unvetted image reaches production. It's your first line of defense against supply chain attacks. Binary authorization adds a critical security gate. After your CI pipeline builds an image, a trusted authority signs it. When you deploy to Google Kubernetes Engine, GKE, Google's managed Kubernetes service, you can enforce a policy that only allows signed images matching your requirements. Everything else is denied. The process locks the door to unauthorized software, so only the code you trust ever runs in your cluster. Here's what nobody tells you about repository locations. If you store European user artifacts in a US multi-region by accident, you could be staring at a GDPR fine. When you create an artifact registry repository, you specify a location, a specific region, or a multi-region, and that determines where your artifacts physically reside. The rookie mistake? Not checking data residency rules, then scattering sensitive container images across the wrong geography. One wrong click, compliance violation. Choose your location carefully. Cloud Deploy defines a delivery pipeline as a sequence of target environments. A typical 3-target progression is dev, staging, and production. You can set up automatic deployment to dev and staging, so each release flows through instantly. For production, you can add a manual approval step, putting a deliberate brake on the most dangerous step. Cloud Deploy orchestrates releases to several target runtimes. Typically, you'll deploy to Google Kubernetes Engine, GKE, GCP's managed Kubernetes service. Cloud Run, GCP's fully managed serverless container platform that runs your containers without worrying about servers. And for hybrid or multi-cloud setups, Anthos, Google's hybrid and multi-cloud application platform that extends GKE to on-premises and other clouds. These targets give you flexibility from fully managed serverless containers to self-managed Kubernetes clusters. Here's how Cloud Deploy separates concerns. A release is a specific version of your deployment artifacts, like a container image and configuration. A rollout is the process of deploying that version to a particular target environment, such as your staging GKE cluster. This decoupling lets you verify a release once and then promote it through dev, staging, and prod without rebuilding. What is the difference between a release and a rollout in Cloud Deploy? Pause and think. Here is a 2-part checkpoint. First, which fully managed serverless container platform on GCP runs your containers without managing servers? Pause and think. The answer is Cloud Run. Second, recalling from earlier. If your production app runs in a single zone, what architectural change helps survive a zone failure? Deploy across at least 2 zones in a region with a load balancer and data replication. This way, you're reinforcing new knowledge and strengthening earlier material in one go. When you start treating infrastructure as code, 4 benefits become non-negotiable. First, reproducibility. The same configuration always builds the same virtual private cloud, VPC, your own isolated network on GCP, along with subnets or instances. Dev, staging, and prod all match. Second, version control. Your entire network topology has a Git history. You can see who changed the firewall rule and why, and you can roll back to a known good state instantly. Third, automation. One command provisions everything without risking a misclick in the console. And fourth, collaboration. Infrastructure changes go through pull requests, so peers review every change before it touches real resources. Once you work this way, clicking Create VM feels like writing raw SQL directly on production. Dangerous. Unlike many GCP services that run inside Google's cloud, Terraform runs from your local machine or in Cloud Shell. It's not a managed cloud service. You write configuration files commonly named main.tf in HashiCorp configuration language, HCL for short. Terraform processes these files and interacts with the Google Cloud API to provision real resources like VPCs, subnets, and compute instances. It tracks the state of your infrastructure, which can be stored locally, though remote backends are recommended for shared environments. This design gives you full control over the provisioning process. Let's walk through a real main.tf file. At the top, the Terraform block uses a version constraint, here a tilde greater than 5.0, to pin the Google provider to a compatible version range, preventing infrastructure breaks from major provider changes. Next, the provider block sets the GCP project and default region. Finally, you declare resources: a VPC network, a subnet, and a VM. Notice the subnet references the VPC's ID with Google Compute Network.VPC network ID. This creates an implicit dependency. Terraform won't create the subnet until the VPC is ready, so the order is always correct. That is the power of declarative code. Let's see the complete workflow. Open Cloud Shell. If Terraform isn't already installed, you can add it with a single command. Once ready, clone the repository that holds your config. Then run Terraform init. You will see it downloading the Google provider. Next, Terraform Plan gives you a preview of the 3 resources about to be created, each marked with a plus sign. Apply with Auto Approve and watch the VPC, subnet, and virtual machine appear in your project. Finally, when you are done practicing, run Terraform Destroy so you are not paying for idle resources. This entire cycle can be a CI job later. Drift detection keeps your infrastructure honest. Terraform stores the desired configuration in a state file. When you run Terraform Plan, it compares the live Google Cloud resources against that state. If someone manually changed a resource, the plan highlights the drift. On the next apply, Terraform may modify or recreate the resource to bring it back in line with the code. That can cause a brief hiccup. So the golden rule is, never touch infrastructure manually when using IAC. Quick checkpoint. You're debugging an issue and manually bump a VM's machine type in the console. What happens when the Terraform pipeline runs next? Pause. Terraform sees the drift and resets it back to the code-defined spec. The manual fix gets undone and the problem returns. That's why the golden rule exists. Never touch manually. Keep that in your deployment playbook. When multiple team members run Terraform at the same time, the state file can get corrupted. The solution is a remote backend, like cloud storage, which serves as the single source of truth for your state and provides locking to prevent concurrent modifications. This diagram shows the flow. The CLI fetches the state, locks it, applies changes, and then releases the lock. You can also enable object versioning on the cloud storage bucket for an extra rollback safety net. The remote backend keeps your state safe and collaborative. Instead of a developer opening a cloud console and clicking Allow All Traffic, every firewall rule change goes through a pull request. A teammate reviews the code, spots the dangerous rule, and blocks the merge. That mistake never reaches production. Infrastructure, as code forces every change through peer review. The same safety net you already have for application code. One review can save your entire database. When you're working across multiple clouds, Terraform stands out. Its declarative HCL syntax works everywhere, and the community provides thousands of modules. Other tools like Google's Deployment Manager are great on GCP but tie you to one vendor. Choosing Terraform future-proofs your career. The skill transfers wherever you go. That checkpoint question was about the Terraform.tf state file. Let's peek inside. The state file is a JSON document that Terraform manages automatically. It maps your HCL resources to real cloud resources. This simplified snippet shows how an HCL resource named Web Server of type Google Compute Instance gets linked to an actual instance. The IDE attribute holds the cloud provider's identifier, bridging your code to the real infrastructure. Understanding this structure will help you debug. Never edit it manually, but reading it is a superpower. Let's check your understanding. Someone manually upgrades a VM in the GCP console. What single Terraform command will reveal that the live resource no longer matches the code? Pause if you need to think. CI/CD and infrastructure. As code are like peanut butter and jelly. Together they unlock the holy grail of DevOps. CI/CD automates building, testing, and shipping your application code. IAC automates provisioning the servers, networks, and databases that code runs on. When they work in tandem, you can spin up a brand new staging environment with a single Git push, identical to production, ready for testing, and torn down when you're done. Adopting both practices together helps teams ship more frequently and recover faster. A hallmark of high-performing DevOps organizations. Let's check your understanding. Why is it so powerful to pair CI/CD with infrastructure as code? Pause and think. The answer. You can spin up a staging environment that mirrors production almost instantly from a code push. That means no more, "It worked on my machine" surprises, and you can tear it down just as fast, saving costs. Cloud Build and Artifact Registry include free tier usage, so you can experiment without checking your credit card after every deploy. Terraform CLI is free, but the cloud resources you spin up might cost you, so stay inside the free usage quotas. Cloud Deploy also gives you a free tier. Your first active multi-target delivery pipeline costs nothing per billing account. So don't just watch this and close the tab. Open Cloud Shell right now, type Terraform in it, and start writing your first main.tf. That's the difference between someone who knows about DevOps and someone who actually does it. If this video saved you from a future production meltdown, hit subscribe and ring the bell. Part 11 drops soon, and you won't want to monitor your monitoring without it. Keep building, keep automating,